Hi, everyone. We've been talking about kinematics, which is the descriptive study of motion. So we've looked at where something is, how fast it's going, how that velocity is changing, what direction it's going in. Um, and that's kind of been our basis for motion now. Now we want to get into dynamics. And dynamics is explaining why motion is changing, why it's happening. And the bottom line is because of forces. And Isaac Newton did a lot of the basis for this. He was not necessarily the originator of the ideas, but he wrote the ideas down and is given credit for the laws of motion. And I know you've covered this in previous years of science classes. So we're going to cover chapters 5 and 6 in this unit. Chapter 5 is Newton's laws of motion, and chapter 6 is how we use Newton's laws of motion and forces. So this is dynamics, the explanation of why things are changing in motion. So bottom line, it comes down to forces. A force is simply a push or pull, which means it's a vector. It has to have a magnitude, an amount, and it has to have a direction. It can't have, you can't talk about a force without talking about the direction that that force is acting in. So there can be many forces acting on one object, but the effect of all those forces is one final effect. So it's acting like there's one overall force, which is what we call a net force. So that's why things change their motion. So first of all, we got to talk about motion a little bit. Let's talk mass first. Mass is not a force. Mass is just a measurement of how much matter there is in an object. And we measure it by how difficult it is to change the object's velocity. In other words, if we have more mass, more force is necessary to change the object's velocity. So um, you can see this table here has a variety of different masses. We deal with masses as large as things like the sun or the galaxy, and as small as viruses and protons and electrons. And so we have a lot of different ways that we look at mass. So the scale that we deal with is 30 decimal places difference. So really large differences in masses, but all of them apply the same way. The larger the mass, the more matter something's made out of, the more difficult it is to change its motion. So the most massive thing that we deal with around us is the Earth. And you can see the Earth is 5.97 times 10 to the 24 kilograms. We know the mass of the Earth, and we'll see why we know the mass of the Earth at a different point in time. But those are different things that we look at. So we look at mass, and mass is always measured in kilograms. That's our base unit in physics. In chemistry, it's in grams. Physics, we measure in kilograms. So when we talk about motion, think of it this way. If you stop pushing an object, does it stop moving? Well, in our experience, it does. And the reason it does is because of friction. But this was a question that was asked in ancient times, and people thought there were a lot of different explanations. One of the explanations was that it moved through a mysterious substance called ether, and that it squeezed through ether. So it made a hole in the ether, and the ether squeezed through it, kind of like toothpaste squeezing it out. Um, so there was an idea that ether flowed throughout the universe, and it went in a different in a certain direction, and one direction was faster, and one direction was slower. And there are all kinds of different ideas. But bottom line is, if we have an object moving, it's going to move indefinitely, or it's going to stay in its state of motion indefinitely. If we push something, it's going to slow down in our experiences because there's friction. And friction is defined as a force that opposes motion. We'll look more at friction in chapter 6 and how we quantify friction, but it's a force as well. All right. So when we talk about, you can see this line here, if in the absence of any net external force, that means any force acting on an object as the object is existing. So if there's no net external force, the object will move in a straight line. It won't change. In other words, moving in a straight line means the velocity stays constant, or it'll stay at rest. When we see something sitting there, we don't expect it to move on its own or out of the blue. When we see something move, we tend to think there's got to be an explanation behind that, and this is what this is the basis of. All right. This is the wording of this is more known as the law of inertia. An object in motion tends to stay in motion in a straight line, and an object at rest tends to stay at rest unless acted on by an outside force. And in general, when something's moving, that outside force is what we call friction, the force that causes something to slow down or change its motion. All right. So we need a net force for something to move if it's stationary, or we need a net force for something to slow down or change its direction if it's moving. All right. So that brings us to Newton's second law of motion. And Newton's second law of motion, of the three laws of motion, is the one that has a numerical quantity and comes down to a formula. And it tells us that the acceleration that an object experiences is proportional to the force. Now we're going to do a lab on that on Thursday and verify that. But we know that if there's a force put on something, it causes something to change proportional to the force. So if we double the force, the object's change in motion is doubled. And that change in motion, remember, is acceleration, because acceleration is based on a change in motion. So if we double the acceleration, as you can see, or double the force here, we see that acceleration doubles. We're going to see a relationship like this when we do the lab on Thursday. All right. We also have found that the acceleration is inversely proportional to mass. In other words, if you increase the mass, the acceleration for the same amount of force is going to decrease by a proportionate amount. So if we double the mass for the same amount of force, the acceleration is going to be cut in half. And that's what this diagram shows us. All right. So that comes down then to this formula. Acceleration is proportional to force and inversely proportional to mass. And that gives us the most famous formula in physics, which is F equals ma. It's usually written instead of A equals F over m as F equals ma. Force equals mass times acceleration. So we can find the net force on something. And remember, the net force doesn't mean any single force. It means the combination of all the forces. So when we talk net force, that will cause one acceleration. All right. So when we see something move, there could be millions of forces on it, but the motion is the result of all of those forces combining to give us a net result. And a net, just like in accounting, is when we take all the forces and add them together. Because remember, force has to have an amount and a direction. So if all the forces add together, it will give us one direction with one amount overall when we add them. Because some forces will cancel out, some forces will add together. All right. So this is our formula. Now you might see, and the book does a good job, I don't usually use these arrows, but these arrows show us that these are vectors. So whenever you see an arrow above a variable, that represents it as a vector. So the force vector and the sigma notation just means it's the sum of all forces. So the net force is equal to the mass times the acceleration that something experiences. So in our unit of measurement, force or mass is in kilograms, acceleration is in meters per second or meters per second squared, and force is measured in newtons. We can also say kilogram meters per second squared. So 1 Newton is equal to the force that causes 1 kilogram to accelerate at 1 meter per second every second. That's what 1 Newton is equivalent to. You can see here the different system of units. The centimeter gram second unit is measured in dynes. We don't deal with dynes. The British unit is the pound. So we know the pound is our unit of force in the English or imperial system. The unit for mass is a slug, which most of us had never even heard of. But we deal with the Newton, named after Isaac Newton because he did so much about force and motion and the effects of force on motion. So these are some typical forces that we see. The space shuttle has an amazing amount of force, and the reason for that is because it's got a lot of mass, and it needs a lot of force to accelerate it to a speed that it can get out of the Earth's gravitational pull enough to go into orbit. A typical jet engine has a lot of force because it has to push that jet along, and those jets are not small. They're very massive. The equivalent of force with 1 Newton is approximately a quarter pound. So we see an apple is approximately 1 Newton because it's usually about 4 apples in a pound. All right, so we can measure force in things. Notice the bottom 4 things here are all weights. Weight is a force, and we'll talk about weight versus mass in the next video lesson. All right. When we do forces, we usually want to visualize them in a way that represents what's happening to an object. So we do what's called a free body diagram. And a free body diagram shows all of the forces that are acting on something, all of the forces that we think are acting on something. And by showing those forces, we can boil it down to what the net force is. So it should help explain the motion of the object. So it's a way to predict it. It's a way to visualize it. So we sketch the forces as vectors, as arrows, showing all the forces that are acting on something, like gravity, like friction, like a surface that it's sitting on. And we look at the forces that are acting on the object that's moving. And then we can choose a coordinate system. Like if something's on a slope, maybe we make that slope one direction forward and one direction perpendicular to that. So we have a forward and upward compared to that slope. We could do it just horizontal and vertical if we wanted to as well. But sometimes we might want to aim it like that. So it's easier mathematically. All right. And then we change it into perpendicular components so we can use SOHCAHTOA and trig and different things to isolate and understand the forces. And then we apply Newton's second law to each coordinate direction. In other words, everything that's acting in opposite directions will cancel each other out if they're equal in magnitude. But if one is greater in magnitude than the other, then the net is in that direction. All right. So we just look and see. And when we add up all the forces, we get one force that is left over when we add them all up, when everything cancels out everything else. And we get that one force, and that's a net force. That's what we apply Newton's second law to. So then we can use that one net force with F equals ma to predict what the acceleration of an object is if we know its mass. Or we can predict what the mass is of the object if we know the acceleration. All right. So this is a free body diagram. We see this book sitting in this person's hand. That person's hand has to be putting a force upward. There's a force downward. Now notice the force upward is equal to the force downward. So this book is sitting in the hand. It could be moving. That does not mean it's not moving. It could be moving, but the motion would not be accelerating. So this could be a book that's being lowered at a constant rate, or raised at a constant rate, or stationary. The arrows do not tell us what's happening to the book exactly in terms of velocity, but it does tell us that the acceleration is 0 because F equals ma. It doesn't tell us velocity, it tells us acceleration. All right, so here's some free body diagrams that I want you to practice on or visualize. So pause the video right now and write these out on paper or on your iPad and see what you think if you've come up with the same idea that these have. All right, I'll give you a little time. Make sure you pause this and give it a try. Okay, so a book resting on a table Well, it's not accelerating, it's sitting there. So the table has to put force on it. We call that a normal force. We'll talk about normal forces at the end of this chapter. And we have the force of gravity downward. So those two forces are equal and opposite. So the book is not accelerating, it's resting. So that is the net force of 0, because the normal force and the gravitational force cancel each other out. A swing that's hanging on its chains. Well, if it's got a couple chains on it, those two chains are acting upward. They're under tension, which is another type of force. So we'll go through the different types of forces that we can label as. And then it's got gravity pulling it down. Now, if we take the two tension forces and add them together, remember the length of the vectors is equal to the amount. The length of those two vectors should add up to the length of the gravitational force, and that should cancel out to give a net force of 0, because it's hanging there. An egg that's falling, all right? We expect that egg to be falling and accelerating down. It's in a vacuum, which means the absence of material, not a vacuum cleaner. So there should not be any friction. So if that egg is falling, we should just have a vector downward that tells us the acceleration is going to be downward. All right. If a car is accelerating to the right, and generally our free body diagrams, we just put a box there. You can certainly draw the car, you can certainly draw the egg. Sometimes it's just a point. In a lot of AP questions, it's just a point on a grid, and you have to draw the arrows that represent the force on that object. All right. They don't have to be really detailed though. These are all valid free body diagrams that you see here. A car accelerating to the right, we have the force from the road upward, we have the force of gravity downward. Those cancel each other out because the car is not going up or down, accelerating wise. We have the force applied by the engine, so applied force, and we have the force of friction, which is road friction and air resistance. All right. Oftentimes we'll have a lot of different free body diagrams that have 4 different forces acting on those. A car moving at a constant velocity, that's going to look very similar, except for the fact that the friction and the applied force are going to be equal to each other. So notice we have a slight difference in these two. The difference is that the horizontal arrows are not equal and opposite. They're opposite, but they're not equal in the one that has an acceleration. Moving at a constant velocity doesn't mean that there's no forces. It means that the forces cancel out. So they're equal and opposite. And finally, a bike rolling to a stop. Well, we're assuming it's moving to the right in this diagram. So there's friction to the left, but there's no force that's being applied to cause it to accelerate or move to the right. So the force moving to, or the friction is causing it to slow down as it moves to the right. So it is undergoing an acceleration, but it's a negative acceleration because it is slowing down in the direction that it's moving. All right. So I wanted to show you those different free body diagrams and have you guys experience that and think about how you would do that. We're going to, generally in this unit, I'm going to have you do a free body diagram for a situation so you can describe what's happening in those situations. Okay, we're going to go to Newton's third law of motion in the next slide and the next lesson. So feel free to take that lesson tomorrow and we'll go from there. Thanks a lot.